Okay, so in this example, we're going to be looking at some spring properties. So basically, springs are something that comes up in physics and engineering quite often because they're not only physical things that exist and that you can put into structures, but they're also things that can be used to model other more interesting physical phenomena, like the interaction between molecules. So springs actually come in quite handy. So the basic principle is you have a spring that has a characteristic spring constant, and a spring constant is usually something that a constant that has parameters of newtons per meter. So the force of a spring is usually given by the spring constant times some displacement x. So you can imagine that if you have some kind of unstretched spring like this, and then essentially what you do is, well, this should actually be negative, and you'll see why. Let's say that this is the unstretched, this is the spring under no compression or tension, and then what's going to happen, let's say that you stretch this spring a little bit, such that now it has a displacement x, then the spring is naturally going to exert a force to return back to its equilibrium position. So, and the same happens if you compress the spring. So let's say you do this to it. Now you have a minus x displacement from the equilibrium position, and then it is going to exert a force to return back to its original position. So the idea is that you're going to get this kind of thing where you have a displacement times the constant. And sometimes we just call that displacement delta, so we can just draw lowercase delta here. And the reason is that we don't want this to be confused with the axis. So if we have our x and y axis, we don't want people to think that we're taking this as our displacement, but rather some actual quantity for the displacement rather than a variable. So if we have a spring system, then what's going to happen is you can imagine that this is naturally going to push it down because you're going to have the following. You're going to have the mass, and it's going to have a weight. So the weight force is going to be mg. Now, what's going to be the force on the spring? Well, naturally, the spring will try, because it is being stretched, it is going to exert a force upwards to counteract that effect there. So let's call this the spring force. So now if we draw this together, basically our equation of motion is going to look a little bit like this. We're going to have some of the forces in the y direction. They're going to be equal to 0, and now we're going to have our force, spring force, and then minus mg, such that our spring force is going to be equals to mg, and we know that Fs is just going to be k delta. So we can actually find the displacement due to this mass and given some spring constant by plugging in the following equation. So we're going to have the following: mg over k. So that is going to give us the displacement in meters from that equilibrium point that the spring has. And this is a really, really important thing. And this basically, this result here usually comes from Hooke's law. So Hooke's, and this is just a linear approximation to the actual displacement of the spring, because the full treatment actually involves higher order terms. So we'll have things like k squared and so on. But this is just the linearized version, and we can imagine that for very, very small displacements, this is actually good enough, and it's actually quite good for performing preliminary analysis on systems. So we'll see in the next few videos that we can actually apply this to the analysis of many systems that involve springs, and they can actually be quite useful for modeling other things, as we'll see later on.